This lecture introduces the reactivity of unsaturated carbonyls. Alpha-beta unsaturated carbonyl compounds are carbonyl compounds that have a degree of unsaturation at the alpha position, and this can be an alkene or an alkyne. We can draw the resonance forms of the alpha-beta unsaturated carbonyl compounds and see that the nucleophilic sites are at the oxygen and the alpha carbon. The electrophilic sites are at the carbonyl carbon and the beta carbon. So if we were to summarize that in one structure, the oxygen can act as a nucleophile, the alpha carbon can act as a nucleophile, and the electrophilic sites are at the carbonyl carbon and the beta carbon. One thing to remember about the character of the alkene in alpha-beta unsaturated carbonyls is that because this alkene is in conjugation with this electron withdrawing carbonyl, this is no longer nucleophilic. This has more of an electrophilic character at the beta position, and this does not undergo the usual electrophilic addition reactions of isolated alkenes. When we have alpha-beta unsaturated carbonyls, we can have two types of nucleophilic addition. We can have 1,2 addition, where addition occurs at the carbonyl carbon, that is the 2 position, or we can have 1,4 addition, where nucleophilic addition occurs at the beta carbon, that is the 4 position. When we compared the 1,4 addition and 1,2 addition processes, the 1,4 addition gives the thermodynamic product, that is the more stable product. And if we were to think about the relative stabilities of the compound, a carbon-oxygen double bond is more stable than a carbon-carbon double bond. And so this is the more stable compound due to the stability of the carbon-oxygen double bond, and that's the thermodynamic product. This is the product of a 1,4 addition. A 1,2 addition gives you the kinetic product, and if you have strong reagents like Grignard's and organolithium reagents, they're going to do a 1,2 addition, and this is what occurs faster than a 1,4 addition. Now let's look at the mechanism of a 1,2 addition. If we do a nucleophilic addition at the carbonyl carbon, we're going to have ethyl magnesium bromide act as the nucleophile, and that is going to do a nucleophilic attack on the carbonyl carbon to give us the tetrahedral intermediate. The tetrahedral intermediate, upon workup, is going to protonate to give us the alcohol. And so our final product is going to be this tertiary alcohol. Overall, we've done addition of ethyl magnesium bromide in a 1,2 addition pattern and formed an alcohol compound. We have not affected this alkene. 1,4 addition is also called a Michael addition or a conjugate addition. If we were to draw the mechanism of the addition of a cuprate or a Gilman reagent, we will start with nucleophilic attack. And so we have nucleophilic attack of the cuprate to the 4 position of the alpha-beta unsaturated carbonyl. We end with this intermediate where we've made a new carbon-carbon bond. This is the new carbon-carbon bond that we made at the 4 position. So this is 1, 2, 3, 4, and we've added an ethyl group. Upon workup, we would protonate this enolate. So upon workup, we're going to treat it with mild acid or water, and this enolate is then going to protonate to reform the carbonyl. overall, we've done an addition at the 4 position, and we have our carbonyl still present. Now let's work through a problem. We've got an alpha-beta unsaturated ester, and we're going to treat it first with a Gilman reagent and follow that with an acid workup. When we treat it with the Gilman reagent, we're going to favor addition at the 4 position. So we're going to do a 1,4 addition, where we are going to reform our carbonyl at the end of the reaction, and we're going to make a carbon-carbon bond at the 4 position. So if this was 1, 2, 3, 4, this is the new carbon-carbon bond that we made. Now let's look at the second reaction. We're using the same ester, and now we're going to treat it with a Grignard. And we know that if we use a Grignard or an organolithium, we're going to favor addition at the 2 position, that is the carbonyl carbon. And since these are very reactive, and this is an ester, remember that we're going to undergo over addition, where we have addition doing a nucleophilic acyl substitution, and then we are left with a ketone that is still reactive, and then finally we're going to do addition until it forms the alcohol after the acid workup. Now pause the video and predict the major product of each reaction. In the first case, we have an alpha-beta unsaturated aldehyde at Grignard and THF at -40 degrees. We know that aldehydes can undergo nucleophilic addition. With a Grignard, we're going to favor addition at the aldehyde carbonyl, that's the 2 position. We're going to make the tetrahedral intermediate, and upon workup, we will protonate that tetrahedral intermediate. And so our final product is going to be addition at the 2 position to make this alcohol. In the second example, we've got an alpha-beta unsaturated ester. We've got an organocuprate reagent in THF for 1 hour from -78 degrees to room temperature. We know that a cuprate is going to favor addition at the 4 position, and so the final product is going to end up reforming our carbonyl and making a carbon-carbon bond at the 4 carbon. And so our final product is going to be this compound. In the last example, we have an alpha-beta unsaturated ester. We have an organolithium in THF at -40. We know we're going to favor addition at the 2 position with an organolithium. So if we draw this compound out, we know that we're going to add to the carbonyl carbon. Since it's an ester, we're going to have over addition. So the first addition will result in nucleophilic acyl substitution, followed by nucleophilic addition. And we will end up with this alcohol and the addition of 2 isopropyl groups.